Professor Richard Henderson, it's a great pleasure to have you here. Professor, you, along with other scientists, made a revolution in structural biology and biochemistry with electrocryo microscopy, and you shared the Nobel Prize in chemistry for that. Could you tell me what is the resolution revolution?
Yes, so that was a name that Professor Werner Kuhlbrandt put forward in the year 2014. He thought this would be a good name. Many people told him at the time that it's not a very good name, but actually everybody likes it. So now we all say, yes, we're all part of the resolution revolution. And the way it happened is that many of us had been working for many years, including Werner Kuhlbrandt. In fact, our electron crystallographic structure of bacteriorhodopsin was really the first unstained structure by EM in biology. Kuhlbrandt's structure of the light harvesting complex was the second one. So we've been involved trying to improve the methodology for 30 or 40 years or something like that. But it wasn't until the new detectors came about 2013 that there was a big step forward. And at that point, in the year 2013, there were only 3 labs in the world that had the new detectors. Our lab was one of them. Kuhlbrandt's lab was the second one. And then David Agard and Yifan Cheng in San Francisco working with Gatan. There were 3 labs. So we had a monopoly for 1 year on the new methodology. And most people said, okay, we're the only ones, three microscopes in 3 labs, until everybody else had a time to get money, order the microscopes, get them delivered. And so people from Britain and Spain, they were the 2 countries, we had them visiting us. Kuhlbrandt had people from Germany, and then Cheng and Agard had people from America. So actually, by the end of the year, there were lots of structures, and then everybody started to buy it. And now the company, they had to increase the number of microscopes from about sort of 7 or 8 up to 50 or 60 a year. But now they need to make them less expensive, which is, of course, the idea that we have. But we're still in the middle of the resolution revolution. And it was only yesterday that Georges Cherez came to tell me that the apoferritin structure, which was the highest resolution, 1.2 angstroms, had now reached 1.0 from this Dmitry Tegunov, who is at, he's in Germany at the moment, but I think he's going to work at Genentech, the company in the USA. So, it's attracted not just academics and people in pharmaceutical companies, but people over a very wide range. So it's quite a powerful method.
Yes, in the number of protein structures being determined by cryo-EM is growing really fast. You showed that. What are the advantages of this technique over others?
The main, well, we've been asked this before, so I know there are 3 main advantages. You don't need to have very much material, so less material than any other method. It doesn't need to be pure, less pure than any other method. And it doesn't have to be as stable or in one conformation, because you can sort those out. So I think stability, purity, and homogeneity are less demanding, and that makes it very powerful. So lots of people, if you're lucky, you can take your sample, make a specimen, put it in the microscope, get data, and have your structure solved in a few days. Whereas by the other methods, X-ray crystallography, you have to make crystals and then go to the synchrotron. So, but of course, you can also have a problem, and then it can take you years to sort it. But it's the same problem. If you can't get crystals, you can't do the structure. And if you can't make a high enough concentration at a high enough temperature, you can't do NMR either. So there are different problems, but if you're lucky, it works really well.
Yes. And what are some of the scientific advances that have emerged as a result of using cryo-EM?
Yes. So as far as I know, there isn't yet a drug that's been designed to cure you of a disease. But people are working on it quite hard. And you have to remember that the X-ray crystallography methodology wasn't adopted by companies for drug design until about 1990. And then it took, maybe 10 years before the drugs reached the market. And, now we have coronavirus.
Yes.
And there are two, there are many drug potential, but there are two main drug targets. One of them is, the main protease of the coronavirus cuts up the proteins. There are 10 or 20, there's a polyprotein that gets cut up, just like HIV. So there is an HIV, there are protease inhibitors that are part of the drug cocktail that can arrest HIV. And similarly with hepatitis C, there is a drug, you take a protease inhibitor and an RNA polymerase inhibitor, and you can be completely cured of hepatitis C in 8 weeks by taking a course of these drugs. HIV, on the other hand, you have to take the drugs for longer. So at the moment, they're still looking for drugs that can help you with, and in all likelihood, rather than cryo-EM drug design producing the drugs, it's more likely that there'll be drugs that are repurposed existing drugs. For example, I just read during the weekend that hydroxycytidine is quite effective. That's just a cytidine homologue that causes an increase in the error frequency of the RNA polymerase in the coronavirus. So it's quite likely that the general power of the biomedical and structure pharmaceutical company will produce cures, but cryo-EM will help, particularly in the long run when you're looking for completely novel structures.
Yes, this method was used to determine the structure of a SARS-CoV-2 spike protein.
Spike protein, yes, exactly.
That was important for the design of vaccines.
Yeah, but there were previously spike proteins done of different coronaviruses done by X-ray crystallography. Particularly, there's a group in America, in Austin, Texas, that have been they were doing it 20 years ago, so it was very easy for them to switch all their methodology. But you're right that the conformation that keeps it in the pre-fusion state, that helped the RNA vaccine drug designers to design the right conformation of the spike protein. And so looking forward, it will help in looking at, let's say, different variants and perhaps producing better antibodies. Yeah, so I think in the area of human health and disease prevention, the cryo-EM will have a big future impact. And actually, one other interesting thing is, we've been doing cryo-EM for a long time, but about 2016, in our restaurant where we have discussions at lunchtime, one day, this is now 2016, 5 years ago, the CEO, Haran Jyoti from Astex, was having a different discussion from a different group in our restaurant. And he came over and he said, I have heard that cryo-EM might be a useful method for us to do in drug design. And at that stage, we were talking to the electron microscope manufacturing company. So we said, okay, sit down. And within 6 months, 5 pharmaceutical companies in the Cambridge area here in the UK had come to an agreement with Thermo Fisher to buy their own microscope, and they've now had it for 5 years. And they've 5 companies, each of them bought 1 day a week, and they shared it initially. But now they have 2 microscopes, so they have 2 days a week shared. But all the companies, all 5 of them, have also bought their own equipment. So it's gone from nothing to probably 8 or 10 microscopes just in the Cambridge area for drug companies. And also worldwide, there are probably about 12 or 15 other companies, still not as many as do X-ray crystallography, but it's really is having a lot of impact, actually.
As you mentioned, these microscopes are still very expensive, and you are trying to make more affordable machines. Will we have cheap cryo-EM in the near future?
Yes. Well, it depends what you mean by cheap.
Yes,
So
sure.
if you buy a Krios with really good detectors, it's about £4 million, say, $5 million. You can get, it's slightly less expensive to buy something similar from JL, but still, 3 or 4 million. So when we bought this one I showed a picture of in the talk, it's only £200,000 for the microscope.
Mm-hmm.
So 20 times cheaper, but it's a very simple microscope. So we had to add field emission gun, and we have to add detector, and we have to redesign. So at the moment, if you wanted one, you could try to ask JL if they will sell you what we've now got. And they will probably say you need to wait 6 months. But the other company, Thermo Fisher, they announced their Tundra, and you can order one now, but the cost of that is about 1 million, let's say, pounds, say $1.2 million. But I understand, because we talked to them, we think 2 people have actually ordered one. And we're supposed to get one here to test at the end of the year. So in about 3 months, we will have one. And so we will have the expensive microscopes plus 2 of the companies that are trying to make them less expensive. So obviously, let's say if you're from a country without so much money, this is the perfect way to go. I would say I think it's guaranteed to work, but it won't work perfectly on the first day. You'll need to keep doing upgrades. So for example, we're working to get better detectors. The detector we have at the moment, which is this one we bought from Dentris, it's like a 1 megapixel. Now you remember digital cameras in the year 2000, you could get a 1 megapixel digital camera, and they weren't as good as film. But now you can get a 50 megapixel camera. Yes. So at the moment, in the 100 kV cryo-EM, you can get a 1 megapixel. And several companies are working to make one that would be maybe 4 megapixels. But to get one that would be bigger, and the ones on the high-end microscopes, they already work with 16 megapixels. So, and that helps you. It means that you need on the 100 kV at the moment, when we do our data, we have to collect 16 images to get the same field of view, and then it takes longer. But usually the time on the microscope isn't rate limiting. The rate limiting time is getting a good specimen, and for that you need daily access.
I will ask you, besides the cost, what are the challenges of the field?
Yes. One of the things you get when you buy an expensive car is it's very easy to use, and it doesn't break down, and it goes very fast, and it's a pleasure. So as you come down in cost, it's less automatic. On the other hand, the cost of one student for a year in the UK is about £20,000. So you could employ a student for about 30 years for the price of one of the inexpensive microscopes. For the high-end microscopes, you could employ a student for something like 100 years. You get a microscope, or you get a student for 100 years. So our idea is that there are plenty of people who would like to learn, and doing it every day, 8 or 10 hours a day, perfect. So, and you can do a different experiment every day. So I think the barriers are, what will happen, it'll be just like other products. So for example, at the moment, if you want to get a new car, you can buy a small, inexpensive car for, you know, £5,000 or £10,000, and it works perfectly. Goes from A to B, you know, as fast as anyone else. It's a bit noisy, a bit less comfortable, but it works. Or you could buy a car for £1 million, you know, and then you have a chauffeur to drive you. So I think what will happen is the cryo-EM will become a commodity, and some people will buy less expensive versions and use a lot of manual labor to overcome the fact that it's not very automated. Other people will buy automated ones. Other people will not buy one at all, but they will buy time. They will lease. For example, you can lease a car for a year or a day. And there are lots of companies now that do contract cryo-EM. But the cost per day, if you work out the total cost of a really good, it's about $6,000 or $10,000 per day for one day. So companies will charge you a bit more than that, probably.
Yes, sure.
So you have to decide: do you need one microscope or 10 microscopes? And a lot of the national facility, for example, the UK National Cryo-EM facility, which is co-located with the synchrotron near Oxford, they have about 10 microscopes like this. And you can go there, you have to book ahead, you know, maybe a few weeks, and you get 1 or 2 days of time. And because it's funded centrally, you don't have to pay. So I think it's a kind of socialist system of access to cryo-EM. And I think that's a good system. But alternatively, you can pay. And a lot of the pharmaceutical companies, they pay for access to synchrotrons, they pay for access to cryo-EM. They don't need to invest in the infrastructure themselves.
Now, changing gears a little bit, have you always been interested in science?
Have I always been interested in science? Not particularly, no. Depends on your background, you see. So I come from the countryside in Scotland, and my father was a baker. He made bread and cakes, and you know, my mother worked in you know, when chickens lay eggs, they lay little eggs, medium eggs, and big eggs. So my mother worked in a what they call an egg grading station, where they sort them into different. They find out, make sure they're all good eggs, and then they put a stamp on it. So you know, so then all I did was I went to school, and I learned, you know, some English, some maths, some foreign languages, and eventually, comparing all the different academic subjects, I thought science was most interesting because it's forward-looking, and anything you discover in science becomes a fact forever. You cannot rediscover it because it's known, it's in textbooks. And then what we're doing is we're building on the foundations. And so when I was at school, the structure of any protein wasn't known at all. Now we know the structure of 190,000 or something like that. And you can't go back. So you're always going forward. So I think science is very, and then if you're a practicing scientist, you're trying to find out something new. And when you find something new, nobody else has known that fact. So it's much more, you know, there's some jobs you go every day. Let's say you're a lawyer and a client comes in and they've got some problem. You have to solve that problem. Next day, there's a new client, but the problem may be the same problem. So you are, you know, it can be interesting, but science, you can, obviously not everybody can choose, because I know there are academic scientists particularly if you've got a funding system where you have to get grants. They apply for grant A, grant B, and grant C. And grant A, this is something they're really, really interested in. It's very, very difficult, and they apply for a grant and they get a, referees say, this cannot be done. This grant is not funded. Then they apply for B. This is quite interesting. They're quite willing to do it, but there are various difficulties. Grant B gets turned down. They also put in grant C. This is a very boring project, which is easy to do, but you can prove it. And so grant C gets funded, and then you get a scientist who would like to do A and B, but unfortunately he has to do C, and then he has to turn that. So I think, although science is interesting, it is in the real world. So you can't always do what you want, but you can do what someone wants to pay you for, but some of the time you can do something else. And then if that project that you would really like to do eventually becomes very powerful and productive, then other people want to do it as well, actually. So I think the key is to try and work in science on things that are not leading to a dead end. So in other words, you do it and then it goes nowhere. It's best to do something that when you've learned this, it opens up new areas, actually. And I think a lot of people are doing that. Very powerful now.
And how did you get into your field of research?
Into the field, you mean?
Yes.
Yeah. Well, I was in physics, and when I was an undergraduate, we had a 4-year undergraduate course, and every year we had exams, but in the final year, you have the final exams where they give you a degree or they don't give you a degree, depending if you have to pass the exam. And one of the questions we had in our, in Edinburgh University, we had, questions, quantum mechanics, optics, different questions, so on. But usually they had a final paper on day 6 of the exams. You had 3 hours, and it was meant to be more lighthearted, where you could. It was an essay question, and so what this essay I remember was, they had a choice of 20 topics. So I thought they had an essay called Time, and I thought, oh, this is a good thing to write an essay about time. And initially, of course, time, there's many people have worked on time. It's, seconds, minutes, hours. And then after a while, I thought, well, time consists of the past, the present, and the future. And of course, you can look up the past in history books, and you can look up the present by talking to people. But the future, you don't know. So I thought the future of physics was the most interesting topic. So then I wrote my essay. It was about the future of physics. And this consisted of having a section on each of the areas. This is about 55 years ago, was astrophysics, which would be cosmology in the stars, particle physics, where you do collision of protons or electrons, which is like at CERN, fusion physics, generating unlimited power from fusing hydrogen and so on, deuterium, has not yet worked to produce power, although the methodology works. Solid state physics, which has produced semiconductors, computers, and so on. And any of these areas would have been perfectly good. They've all been very successful. But I thought biophysics, which is essentially International Union of Pure and Applied Biophysics, I thought biophysics was a good one to go into because you didn't need a team of 1,000 people, in CERN or fusion physics or sending satellites or rockets to. You need a team of 1,000 people, but biophysics, you can do it with 1 person or 2 people. So I thought biophysics was a good thing. So then I looked around for a biophysics department in the UK. I didn't want to go abroad until I was older. And I found King's College London, Norwich, Leeds, various places. And I wrote to all of them saying, could you do a PhD in biophysics? And for example, Leeds and Norwich said, no, you cannot do a PhD. You have to do an MSc first. And I thought, well, I've done enough exams. I don't want to. So I eventually decided possibly I would go to King's College in London. But then I told our professor in Edinburgh, he said, oh, no, he said, not King's College London, you should go to Cambridge. So when I came here to this lab, it's now, let's see, 1965. That's now sort of 56 years ago. So when I came here, everyone is working on Saturday. So I came on Saturday, they're all working. So I thought, this is a good lab. So I came here, and then without a plan to do anything other than biophysics. And then when I arrived, it turned out that in MRC, molecular biology, biophysics means structural biology. So I sort of ended up starting in structural biology, and then it looked like it was a method that was going to be become quite important. So I just continued, but changed the way you do. So I originally did X-ray crystallography. Then we did electron crystallography on much smaller crystals. But then it turns out the great power of electron microscopes is not crystals. It's actually taking images without any crystalline order at all. You can use it on crystals, but you can also use it on single particles. And that's where the real power of the current methods are coming from. And then tomography is the next step.
Okay. Very interesting, your story. How important is it for you to participate in the 20th IUPAB Congress in Brazil, though virtually?
Yes, well, I mean, I'm a big, so the first talk I ever gave when I was very young, I was about 21, I went to London from Cambridge and I gave a talk at the British Biophysical Society, which was about 1968 or so. And then later on, I went to the Biophysics Congress in Copenhagen. And since then, I've probably been to about 5 or 6 biophysics congresses. And actually, for 12 years, I was one of the editors of a journal called Quarterly Reviews of Biophysics. And Quarterly Reviews of Biophysics used to be from 1962 to about 2002. So for 40 years, Quarterly Reviews of Biophysics, published by Cambridge University Press in Cambridge, it was described in the introduction as QRB, Quarterly Reviews of Biophysics, is the official organ of the International Union of Pure and Applied Biophysics. So the journal that I was involved with was, but actually it turned out that the way it was set up, the journal was owned by Cambridge University Press, and IUPAB wanted money. So they started their own journal now. So there was a parting of the ways. But yeah, so I've been involved with biophysics in the UK and the International Union and the journal for all my career, actually. So I always think it's a good idea. When we were doing QRB, we always had our meeting at the International Union of Biophysics, whether it was in Vienna or in Kyoto, or, I think they had a meeting this morning of their new journal just before this meeting started in probably virtually in Brazil again. So yeah, so it's a very good meet. I mean, it's not as big as neurosciences or cancer. There's a community of about, I'd say, usually it's between 1,000 and 2,000 people go to the meeting. And I went to Edinburgh, of course, which was in Scotland. And then I would have been there in Brazil, and maybe next year instead.
Yes.
So it's a great meeting, and it covers a wide area. But it's probably not, it's not biochemistry has a bigger impact and group of people. Chemistry is very broad in that they try to include everybody else. And then the various kinds of medicine have a lot of human impact on humans. So biophysics is a kind of caught between all these other areas. But there are people who think it's still a very the methods that it brings to bear on a range of projects is very important.
Yes, yes. And what's your advice for young scientists?
Yes, well, my first advice is to be a scientist. And for that, you need to persuade someone to pay you.
Yes.
So sometimes you have to compromise, but my view is you have to do something you're interested in, because if you're doing research, or even if you're just doing more routine work, things do go wrong. And if you're not interested and things go wrong, it's very discouraging. But the thing I remember from Fred Sanger, who was a scientist here, and he died a year or two ago, he had 2 Nobel Prizes, both of them in chemistry. He used to say that it's important when you're doing experiments not to try to do something that's too easy, because you don't learn very much. You should try something that involves a big step forward. And he used to say you should aim for 99% failure, because then when you do make progress, it makes a much bigger impact. So I think my advice is, if you're a young person, you definitely want to do something that is intrinsically interesting to you from the background that you have. And obviously different people come from different backgrounds. Some people, have personal experiences, either from relatives who've had a particular disease or ailment, or other people they know who have had particular interests. So, for example, my grandfather made clocks. Not very, that was his hobby, and he was a sort of silversmith. And so in our house, we have a homemade clock that's, it has a glass dome. It's a skeleton clock. And so, the knowledge that there was someone in our family history that had an interest in construction projects, that was slightly interesting for me. Now, different people will have other things that are give you a sort of echo of something of interest. And I think that's the most important thing. The other thing is Peter Medawar, who was another scientist originally from Australia. He also said, he wrote this book, Advice to Young Scientists, and another one called The Art of the Soluble. So the idea was science, when you're doing experiments, you shouldn't do something too easy because it's boring, or too difficult because you'll die before you solve it. You should pick something that's at the ideal stage, so it's a soluble problem. So just like in politics, you have to do something that's possible. Yes. So politics is the art of the possible, science is the art of the soluble, and that was Peter Medawar. So you have to do something you're interested in, and also something that in the timescale of the funding that's available to you. For example, if it's a PhD, you need to think of a project or choose a project that will come to fruition in 3 or 4 years. And then after that, you might have a 5-year grant, then you can try something a little bit longer. And then if you've got, let's say, some funding from Bill Gates, you might be able to go a bit longer.
Okay, thank you very, very much, Professor, for joining us.